Hello, students and YouTube viewers. Dave Soriano out in Western Pennsylvania, USA. I'm a chemistry professor at the Bradford campus within the University of Pittsburgh system. And I'll be teaching organic chemistry via remote lecture and Organic 1 lab. Organic Chem 1 and 2 lecture courses this summer via remote. I've been teaching a remote course or two online since 2001. It's nothing new for me, but organic chemistry requires very, very special handling and thought. In this video, I briefly want to introduce you to an aspect of stereoisomerism that is very important in organic biochemistry, molecular pharmacology, synthetic biology. I guess you get the picture. Very, very important. Now, carbon stereos, Greek for 3D, space, solid. Or carbon stereochemistry is generally far simpler than what inorganic chemists encounter, X-ray crystallographers with the periodic table with elements other than carbon. We are focusing on the three-dimensional aspects, fundamental aspects of stereochem. Now, 19 of the 20 amino acids found in proteins and life forms are chiral. That is Greek for handedness, chirality. And all proteins from life forms contain only what organic chemists call the S amino acids, large S. The large R, the right-handed ones, are not found in proteins. They can be found isolated in the human system, but not as part of proteins from life forms. Now, after the death of an organism, racemization, that means conversion, thermally, let's say, or by other means, you will start to be able to break bonds and interconvert the R and S, the right and left-handed forms. Let's not worry about that now. We're just getting the basics down. When I was an undergrad, I'll be 67 in June, stereochemistry had enormous potential, going back to the founding father of the field, Louis Pasteur. But we didn't have platforms, chemical visualization techniques, rendering, and it was very difficult. We had one ball and stick model for 100 students. It was like driving in a whiteout. Now, the good news is for the average student, organic chem, fundamental stereochem is not difficult, but you just have to make sure that you understand clearly the fundamentals. And that does require time. Now, I'm going to do something a little bit unusual, but not really. I'm going to introduce you first to the so-called Fischer projection. Now, you see what I have in the under the camera is a cross. The horizontals are atoms A and B. And then we have the vertical C and D. The center of the cross is an sp3 hybridized carbon. Now that's what you're looking for. An sp3 hybridized carbon with 4 different atoms, groups attached. And this can be very tricky. For example, look up some natural products like morphine, cocaine. Examine them carefully and determine how many sp3 carbons have 4 different groups. And you tackle that one atom at a time. In other words, let's say you're driving to New York City from Philadelphia. There may be one major prescribed route, but there could be alternative routes to get there. You could take the long way around and cut through the Pocono Mountains in eastern Pennsylvania. Okay, or you may take the direct route, let's say the New Jersey Turnpike or even the Garden State Parkway. You have to examine all four A, B, C, D for the entire molecule and make certain all four are different pathways. Now, if you have a hydrogen and a chlorine and a bromine and an iodine, that's easy to tell. You have four different elements, halogens. But when you look at certain molecules, you have to make certain that all four pathways are unique. And that requires you looking one atom at a time until you can ascertain that situation. Now, what I'm showing you first is the so-called Fischer projection. I believe this is probably named for the great organic chemist Emil Fischer, Nobel Prize winner. There were a number of Fischers, but I believe this is Emil Fischer. Now, this notation is used in organic and biochem, particularly by those working with carbohydrates, sugars, because those compounds oftentimes have a lot of chiral carbons. Now, you can encounter antibiotics that could even have 30 or 35 chiral carbons. That many. And it can be rather commonly observed. We're going to start with something nice and easy, and then you'll be amazed at how fast you can progress to a high level. Now, the Fischer projection is a cross. And this actually has three-dimensional information built in. Now remember, A does not equal B, does not equal C, does not equal D. There is three-dimensional information built in there. Now, if you have two chlorines, a CH3, and a bromine, that would be an achiral carbon because you have two chlorines. So once you know you have four different atoms or groups, one atom at a time, then you have a chiral carbon. Now, there is a term we're going to use in this field called the steering wheel. The steering wheel is a methodology for determining whether you have the left-handed large S or the right-handed large R. Now, in biochemistry, the scientists there will use large D and large L. That's often found in biology. Large L is equivalent to organic chemist's large S. Large D is equivalent to large R. S means sinister or left-handed, which I happen to be. Now, there is a little d and a little l, dextro and levo, but that has to do with optical activity, which we will not look at in this film. I'll have another. So don't you worry about little d and little l. They're getting away from that, incidentally. And I'll talk about that in another video. Now, here's what I want you to consider. We have this chiral carbon. There are four different atoms or groups attached. It is definitely left or right-handed. The question is, which would it be? Well, it depends on the nature of A, B, C, and D. Let me now give you this specific example with the cross. H, bromine, chlorine, CH3. We have a winner. H, bromine, chlorine, and carbon. Not CH3. You only use tiebreakers as needed. Carbon. Now, you apply the Cahningold Prelog rules. And these are rules used for determining the priority of atoms. You go by atomic number, atomic mass. Number one group here is bromine. On the periodic table, that has the largest mass. Number four, often, very frequently, but not always, is hydrogen, least prior. Then we have the chlorine or carbon. Chlorine is going to be number two. The carbon with the three H's will be number three. So we have established the priorities for this cross. I strongly recommend that you use ball and stick models. If you don't have that, and of course with the pandemic, we have very bright young people coming up, and money is a serious issue for many families now. If you can, use 4 toothpicks and 4 gumdrops gummy bears. Just roll up those and warm those gummy bears up in your hand, or get gumdrops if you can. This will help you enormously. Now, someday, many of you, when you leave organic, you will not be using the ball and stick model. You're going to be going on to programs, platforms, like I use Wave Function, Sidegress, Chem Office, routinely. And there, I can draw a structure. I could draw a Fischer projection. It will automatically determine for me if it's R or S. But you don't have access to that right now. So you have to know this the old-fashioned way, the way we all did. But later on, you'll be looking at compounds with 3, 4, 5 chiral carbons, and you'll be able to determine with the computer very quickly if each one of them is R and or S. Okay, now what do we do next? We know the 4 priorities. We assign colors. You must have a carbon, here I have black, with 4 different colors: blue, ivory, green, and red. Whatever 4 gumdrops you have, it'll get the job done. Now, I am going to assign the hydrogen the ivy color that I have. I am going to assign the bromine red. I am going to assign the chlorine green. And finally, I have blue for the carbon with the 3 H's. Now, on homework or exam, you do it this way. Some professors will not let you use models, others will. Visualization's getting better and better. Some people are extremely talented at 3-dimensional perception. They will go into dentistry, mathematics, engineering, architecture. But with practice, all of us can become reasonably competent. This area of organic I disliked the most when I was an undergrad, and I wound up publishing papers in this field using chemical platforms, and it's one of the most exciting fields and most important. Now, this is what you do. You've assigned the colors. You are going to grab, this is called the steering wheel approach. You're going to grab the least prior one, which is the hydrogen, number 4. That's ivy. You hold that one. Now I'm going to zoom out so you can see this whole situation. I'm glad I washed my hands before this video. I did grind up coffee. I'm holding the hydrogen, which is number 4. That leaves you with 3 others, a steering wheel. Now listen carefully. You go from number 1, red, bromine, to number 2, which is green, to number 3, which is blue. And that, my friends, is clockwise. Red to green to blue, just like the hand on a clock. Oh boy, they have digitals nowadays, huh? But if you look up in a museum, you'll find clocks with hands, the little hand and the big hand. Okay, number 1 is bromine. Number 2 is chlorine. Number 3 is bromine. You're holding the ivy, number 4. And I told you that's clockwise, to go from big to middle to small. Because it's clockwise, the structure that I have is right-handed. Large R. I just put an R in there. Let me zoom out, or zoom in. Okay, we're getting there. We're getting there. Okay, large R. This is a right-handed isomer, stereoisomer. Stereoisomer means 2 compounds that have identical structures, but the orientation in space differs for what's attached. So this is the right-handed molecule. Now we're going to use another term, enantiomer. E-N-A-N-T-I-O-M-E-R. Now make certain you pronounce that correctly, because someday you're going to be going for a job interview, graduate school, college interview, whatever, and you want to speak clearly and intelligently. Enantiomer. By definition, enantiomers are stereoisomers that are mirror images of each other, but not superimposable. Hence, left and right-handed forms. The structure that I drew here, the Fischer, had three-dimensional information, and now you and I know that if we know A, B, C, and D, we can determine it. And the one that I built with hydrogen, bromine, chlorine, and methyl, CH3, is the right-handed. If you were to break bonds and change these, by trial and error, you'll eventually build one that will be the left-handed, large S, which would have counterclockwise movement. Now, I don't want to do too much in each video. What I will do is make a part 2 for this. But with this clock business, let's go back to it. Here I'm holding the hydrogen, leaving the other 3. Now, I and you, we are standing in front of this clock. We are in front of the clock. And we, by applying the steering wheel, can tell it's R, right-handed. I want you to fine-tune your knowledge. What you will then also practice is standing behind the clock. Turn it this way. Now the least prior hydrogen is pointing at you. It's still going to be right-handed because in your mind's eye, you're behind the clock, but you're proceeding from red to green to blue, and that is clockwise. Just keep in mind you're standing behind the clock. In other words, I want you to look at these problems forwards and backwards. You will then create a clear mental image in your mind. Some people very quickly can apply this knowledge without any models. They have tremendous spatial configurations. In their mind's eye, they can do this. With practice, you may very well be able to do it. Make a note of whether this comes easily to you or not, because that will help you with career decisions. Now, what I will do in the second, I'm not going to get into aspects of how do you separate right and left-handed enantiomers. That is within the domain of lecture with another topic, another video. What I will do in the next video, part 2, is show you the steering wheel approach with solid and broken lines. And that's mostly used by organic chemists. Solid and broken lines is very often what we use with chiral carbons to be able to tell someone else whether we're working with the right or left-handed form. Okay, so here you saw the Fischer, and in part 2, we will enable you. Well, let me do it right now. What the heck? Let me do it right now. Let me turn this around. Okay, I just happen to have this. Okay. Now, let me magnify this, and you can see what I'm drawing here. Now I have a chiral carbon. You see the sp3 carbon. And let's assume A does not equal B, does not equal C, does not equal D. Hence, we have a chiral carbon. Oftentimes, we put an asterisk on that carbon, to denote chiral carbon. So I'll write that down. Asterisk equals chiral carbon. You may have 1 in a molecule. And if you do, then you have a chiral molecule. Chiral atom, chiral carbon, chiral molecule. Now, this is the denotion. We denote symbolically right and left-handed and organic this way. We use solid and broken lines and then 2 arms. Now here, the broken line means carbon here is bound to D. D is pointing away from us. The solid line means C is pointing towards us. And then A on one side, B on the other. Now I'm going to show you how to do it. Let's make the A a hydrogen. Let's make the C, letter C, let's make that a bromine. Let B be chlorine, and let D be CH3, like we did with the Fischer. Okay, now we're going to assign colors. This time I'm going to let the hydrogen be blue. I'm going to let the bromine be green. I'm going to let the chlorine be ivy. And I'm going to finally let the carbon with the 3 hydrogens be red. Okay. Now we're going to build it exactly as shown. This is important. We want the red one pointing away. Okay. I'm pointing it away. The one that we want towards us is green, and I happen to have that. Red pointing away in green. Okay. Now on the left side, blue for the hydrogen, and on the right side, ivy for the chlorine. Okay. I'm going to back away, and I've built it correctly. Now you may say to yourself, what happens if I turn it? Did I change it? No, because I didn't break the 4 bonds. I've established configuration. Just like in basketball, when a player on defense establishes a position, there can be a charge or offensive foul if an offensive player with the ball moves into the defensive player who has established position. So here we have established position. All we're doing is rotating, but we're not breaking bonds. We've established configuration. Okay, now, $1 million question. Is it left or right-handed? Okay, here is your priorities. Number 1 is bromine. Number 2, chlorine. Number 3, the carbon with 3 H's. And finally, the hydrogen, blue, 4. What you're going to do is apply the steering wheel. Hold the least prior one, blue, hydrogen. Now, your number 1 group is green. Your number 2 group is ivy. Your number 3 is red. You're going counterclockwise. Green, ivy, red. Counterclockwise. Counterclockwise. That is the left-handed or S configuration. And that's the ball and stick model. You just make certain to establish solid and broken lines, and then put in the blue and the ivy, just the way I showed you. You'll never go wrong. Then you can turn that, rotate it, whatever you're going to do, but the configuration is established. In organic, we generally use solid and broken lines. In carbohydrate, biochem, and organic, because there are so many chiral carbons, they often use the Fischer. For example, I'll finish this lecture by showing you this. I'll zoom in. And I know out there's probably some 10-year-old kid who is going to be a future Nobel Prize winner in biology or medicine or chemistry. You never know what young person is out there learning rapidly. Now I'm going to show you this with a Fischer. Here I'm going to put in what's called an aldehyde group. Now that carbon is not sp3. Okay. That's an aldehyde group. Here I'm going to put an OH and an H. Here I'm going to put an OH and an H. Here I'm going to put an OH there and an H there, and finally a CH2OH. Now this is what's called a Fischer projection across for a carbohydrate, a monosaccharide, a basic sugar unit. Okay, this is a chiral carbon, this is a chiral carbon, that's a chiral carbon. The bottom one, CH2OH, is not. It has 2 hydrogens. The penultimate, that means next to last, is chiral. The one above it is chiral. The above that is a chiral. Now there is a formula called 2 to the n rule. N is a whole number. That will tell you how many total you can have. Possible number of isomers. that you can have for a structure. Now here you have 3 chiral carbons. So that's going to be 2 to the 3. So that will be 2 times 2 times 2. That means a possible 8. Possibly 8 stereoisomers. Well, what can they be if they're not enantiomers? Another stereoisomeric term, diastereomer. I'm not going to talk about that now, except to tell you that diastereomers are stereoisomers that are not mirror images of each other. Enantiomers, by definition, are mirror images of each other and non-superimposable. So if you have a stereoisomer with the same structure, but an orientation that differs for one of the chiral carbons, then that would be a diastereomer. So for this structure, there's a possibility of 8 stereoisomers. Are there? Well, some of them, yes, for this structure. Some of them are naturally occurring. Some are not and have been manufactured in the lab, synthesized. There are common sugars and rare sugars. But you see, the Fischer is used very quickly to show another person how many chiral carbons there are. Now, you'll be using, when you get done with beginning organic, you'll be using chemical platforms all the time. And you'll draw a structure, put in your solid or broken lines or a Fischer, and it will process it and tell you for each chiral carbon present whether it's R or S. I hope this helps you a tiny bit. It's a very important field, and you want to know your fundamentals. Now, suppose you have, and 90%, 95% of organic chemistry students don't know this. Excuse me. Suppose you have 5 chiral carbons. Okay? 5 chiral carbons. Carbon asterisk. Suppose it turns out it's RSRSS. Now, how do they know this? X-ray photograph. That's one way. So let's suppose for a pure compound, they determined there were 5 chiral carbons, and they happened to be RSRSS. The enantiomer must be all equal but opposite. So it would be SRSRR. So that would be enantiomer 1, and that's the mirror image non-superimposable E2. Okay? Now suppose only one changes. So suppose we have SSRSS. What is its relationship to the top 2? It's a diastereomer, which I'll call D1. A diastereomer is a stereoisomer very closely related to enantiomers, but not a mirror image non-superimposable. Diastereomers can be separated from enantiomers relatively easily because, you see, they have different physical properties like solubilities, melting points, boiling points. Enantiomers, in general, have identical physical and chemical properties except for the ability to rotate plane polarized light. However, biologically, they can have different properties. So you have a lot of reading to do in stereochem, and all I'm doing in this video is helping you to set the table with understanding and appreciating the importance of three-dimensionality in modern organic chemistry as you prepare for upper-level courses in other areas of molecular science. Organic chemistry, indeed, is an introduction to molecular science. Thank you so much for watching. I hope Tiny Bits helped, and you take care. Bye for now.